Okay guys, now we are going to be discussing some of the supplemental materials that are not covered in the textbook. This is the first lecture will be our universal modeling approach to system dynamics. As we discussed in the class, the systems can be viewed as any collection of elements put together doing some actions that are important to us. So we show the system with a black box, and there are some actions as a response of the system. Sometimes we'll call them outputs. That is important to us. We want to look at that output, and we want to, for example, compare the performance of the system by observing such signals. Most systems are designed to take some external user excitation, stimuli, inputs that we show it here as another signal that drives that has at least some influence on the response that we are looking after. Now, in this class, we are going to be studying different domains of physical systems, and let's dive into some principle understanding. For example, in each domains of interest, such as electrical systems or mechanical, translational or rotational maybe, or hydraulic systems, or thermal systems, we will have some variables that we wanted to show the information of the energy flow or information about the system state or performance, which we called some variables. There are a definition of principal variables that is used in that domain. For example, to model a component or a system. So let me write here the principal variables, and they will be independent, and they will have two classes. One is one class of principal variables will be used or will make any sense if they are addressed to with respect to a reference. We will call them relative. Sometimes we call it I'm going to erase this part, and let me do this. Across variables, and the other class of principal variables that are independent from the relative ones are flow, or sometimes we call them true variables. Now, what we are going to be doing with respect to relative and flow variables, we'll try to get the mathematical relation to represent the behavior of a component in that domain, or if there's those components put together, they make a system, and we'll try to make some input-output relation that shows the time response of the system using these variables. Okay, let's put a pause here. As an example, let's look at this vehicle or vehicle-looking car type of vehicle. It has 6 wheels, and we'll try to see that from systems point of view. I can also describe this as a system that might have some outputs of interest. For example, that might be a velocity of this vehicle might be important to me, and I'm going to try to model this car's velocity and the input that may influence the velocity might be the gas pedal or the throttle that determines amount of the voltage or fuel intake to the engine that are supposed to increase the velocity. So this might be an external signal applied by the user driver. The throttle signal can drive this system, that is my car. I'm gonna put another. This was our car. Yes, okay. And the velocity of this vehicle might also be influenced by some other external signals, such as brake. If I want this model to include the effect of the brake, I have to put this as another signal to my system. Now I will have more than one input and one output for this model. We can increase, we can put more signals, more external disturbances and effects to the model to make it look like more realistic and more better fine a model that represent that shows a better relation between input and output. Absolutely, the velocity is not the only factor output of this car. For example, the range of car that it can go with the full fuel might be another signal that is important to us, that defines the performance of the system, and I can put this another input. Or for high performance cars, the acceleration maybe another output or response of this vehicle that are important to some class of users. So now we end up getting multi-input, multi-output MIMO system for this vehicle. Certainly the inputs and outputs might be more than this. However, for this class we are going to be looking into only a single input, single output system. And these systems will be most of the time dynamic, and they will be always linear and time invariant. If they are not, we will try to linearize it and then obtain LTI system, and then carry out our modeling and analysis technique that we are going to be learning in this class. So our interest is to obtain a model of LTI system with one output and one input. Since the system is assumed to be linear time invariant, if there are more inputs, it can be applied to it as a superposition technique. All the inputs are set to 0, only you have one input and one output of interest that you are trying to find input-output relation. MIMO system for LTI can be studied without losing any generality as a SISO, single input, single output systems linear combination. Alright, let's put another pause. Typically, the modeling process, analysis process, will start with an actual physical systems. In the previous example, we had a car, and we are just focusing on one of the responses influenced by one of the input, single output configuration. We will try to make a model of it. To do that, we try to get that picture in a simplified form using the basic building blocks of the system, physical system. For example, if I'm going to be analyzing translational mechanical modeling of the system, I'm going to be using basic building blocks such as mass, spring, damping element, and the external sources put together. It will give me something called schematic. So in order for me to show that, for example, let's say that we have a spring here and then applied to a mass, and there will be an external force here and another spring with a damping mechanisms connecting this mass to another mass, and we might also assume that there is for this example, another mass, a spring here. Let's call this one K1, D1, K2, K3, M1, M2. This will be a particular subsystem, and let's say that the position X2 and X1 of these masses are internal signals, and we are after X2, and we take this as my output signal Y of t. I'm going to try to make external input applied to the system, U of t being F, X2 being Y of t. So it will look like our single input, single output system F and X2 is a block diagram representation of this mechanical schematic of the vehicle that we are trying to model. Again, one more time, our assumptions here, we are working under linear time invariant systems. All the components here are assumed in the region of operation. They show the linear behavior and they are time invariant. If this is the case, then we can come here and we can say that using a set of system plus component equations to obtain a model as A of s times, let's call Q of s equals B of s. Here A is an n by n matrix and Q is all the variables that can be seen in the system is equated to an external inputs added to the system. In this case, this vector is only a function of f. Now, when we talk about the modeling, let's talk first analysis. Given the external inputs, we want to solve or find all of the variables in this domain. If this is a mechanical system, we can take such as positions, velocities, forces in each component, in each element can be, if they can be found, if we know how much force applied to the system. What we have done, we analyze the system. Now we know everything needs to be known about the component at that particular input given to the system. When we talk about modeling, we will make this analysis a little bit more generic to any kind of arbitrary input. So modeling for us will be for any arbitrary input U of t, find an expression, a mathematical expression that shows me what the response Y of t will be. So Typically, for mechanical systems, we use Newton's approach to find this set of system equations, or we can use Euler method, or there are some other techniques. They are basically driven conservation of energy and mass properties. For other classes of the system, such as electrical one, we might have some electrical circuits as shown in this PCB board. In typical process of PCB board generation, we already have a schematic available, and we do the same thing here, taking external source, get an external source applied to a system, and we might have some basic components such as inductors, capacitors, and resistors applied such as R1, R2, R3, L1, C1. This might be C2. This is going to be our schematic of the actual physical system, and again we obtain a set of equations using Kirchhoff's laws. They are also driven based on conservation of energy, and we do the modeling and analysis the same way. If we are given a specific input applied to these electrical circuits externally, and if we find all the currents and voltages, what we are doing an analysis. But if I try to model the system again, I need to find out the input-output relation. External input is shown here. The output is again defined by the application or the user. If we take the voltage across the capacitor C2 as an output, that might be one option, or some of you can take the current that runs through the inductor L1, might be also another output of interest. We'll look at the input-output relation and we'll try to model it, and this gives us a set of linear equations in S domain given by A matrix times Q vector. Q vector is composed of all the voltages and the currents in the system, equals to external sources such as voltage or current source applied to the system. Similarly, for other class of system, we have a similar approach. I need to stop here to move this guy. If you are working with the hydraulic systems, the process is almost the same. We have this actual physical system and we try to model it, and when we look at the operation of it, let's say that there is a pump here applied through a valve to a tank. That has another pipe, a resistor, and another pipe, and that we get this physical system, another hydraulic systems kind of schematic view. Here the difference is actual physical systems are simplified or depicted by some basic building blocks such as tanks, such as pipes or valves to the system, and we end up getting a simplified linear system that shows the operation applied to pressure or hydraulic flow rate to the system, and we'll try to find out input-output relation. This also is the same approach, giving me the same set of equations. Basically, using conservation of mass and energy linear set of equation in S domain, and let's make this as S times QFS, and we do the analysis. If you find out what the QFS is, A of S inverse times B of S operation. This is the analysis part. If you try to find out Y of S is a function of U of S, this is what we call the model. So this is a model, of course, in S domain. This is the analysis result in S domain. If you want to go time domain, we need to get the inverse Laplace transformation of these signals, and we get the result. For the model, to get this time response of the system, we need to have a specific input in mind. U of S should not be a generic, but it should be an actual one. Now, when we look at the techniques that we use for analysis and modeling, we see that we need to get a matrix inversion A in inverse in order for us to solve this such a problem. So to be smart about it, we try to make this solution as feasible as possible. We look at what kind of equations we have here. From the linear algebra, we know that the equations that we have, A times Q equals B, Q being an unknown, A and B given, can be solved if these equations are linearly independent, and A inverse matrix will exist, and from there we can get a solution. So for us, one of the smart approaches is to find the minimal independent variable in the system and then solve them first, and then we obtain independent variables results, and then use the other dependency equations to find all other variables that we are going to be working with. So the techniques that we have seen in electrical circuits in Kirchhoff's node or loop equations basically giving us a hint, a way, an approach to find the minimal number of unknown solutions. Okay. In order for us to analyze physical dynamical systems, we said that we need to focus on only independent principal variables. From electrical circuits course we have taken previously, we've seen that Kirchhoff's guy said that in any electrical circuits, node voltages are independent. Means that if you know the node voltages in any electrical circuits, now you know anything needs to be known about the circuit. All the voltages and all the currents of each components can be calculated using dependent equations. Similarly, he said that the loop currents in electrical circuits are independent sets of principal variables, which means that if I know all the loop currents in any electrical circuits, then I know everything needs to be known about the system. So let's write this down and then proceed. Okay, now I have written here the two main theorems to get us minimal equations to solve to complete the analysis. We said that I'm now generalizing the Kirchhoff's laws that we know from electrical circuits course. Instead of saying the node voltages, I am using the term node relative variables. are independent variables in any physical domain, or in any physical domain, the loop flow variables in electrical circuits corresponding to this loop currents are independent set of variables, which means that if I can solve either node relative variables or loop flow variables, I'm able to find out everything needs to be known about the system, complete my analysis, and carry out with my modeling requirements. Now, if you go back to previous examples, now here we have a bunch of systems, and once we have this system defined, after the schematic, we will try to obtain a graph representation. So let's type here for example, for this electrical circuits, we are going to put all the nodes here. Let's call this one 1, this node to be node 2, this node to be node 3, and for the relative variables, we need to have a reference. Everything will make sense to reference. If I make this node, let's call 0, or my ground, I'm going to find out everything, all the node voltages with respect to this node level potential at this node, which I call as ground or node 0. Therefore, I have node 1, node 2, and node 3 here with respect to ground. Between node 0 and node 1, I have this voltage source Vs, and between node 1 and node 2 I have component R1. Between node 2 and ground we have C1. Node 2 and node 3 we have two components, R2 and L1. Then node 3 and ground we have C2, and between node 3 and ground we have another component, R3. Now we ended up getting a graph representation. As you notice that I put some arrows here. Now let's forget about these arrows for time being. When we are talking about doing analysis using only node variables, we don't need to specify the flow variable direction. We will come to it when we talk about the loop flow variable based on analysis. Regardless of the domain of physical system, it can be mechanical or electrical or hydraulic or whatever, as long as they are linear and time invariant, we are going to get this schematic, and if we obtain this graph representation, this guy, once we have it, after that the set of equations we need to create will be independent of the domain of interest, which means that I don't care at that point if I'm using Newton's law or Kirchhoff's law or conservation of mass, conservation of energy. We will always get this set of equation using our universal approach, regardless of the mechanical or electrical or hydraulic systems that we are making our analysis. Now let's go back the discussion here.